Nanoscale heat engines are microscopic machines that convert thermal energy into mechanical work, operating at scales smaller than a grain of sand. These engines harness principles from both classical thermodynamics and quantum mechanics, making them fascinating tools for understanding energy conversion at microscopic levels. Unlike macroscopic engines, nanoscale heat engines operate in environments dominated by thermal fluctuations and quantum effects, challenging traditional thermodynamic laws. For instance, a nanoscale engine powered by laser heating can drive a single trapped nanoparticle to oscillate, converting heat into mechanical motion. This is akin to a steam engine so small that instead of coal and water, it uses heat from individual molecules to push tiny pistons. These engines rely on the interaction of particles with thermal gradients, leveraging processes like Brownian motion or optical trapping. Operating at such small scales, where thermal noise and quantum coherence significantly influence performance, the energy from a single thermal fluctuation can drive the entire system. A notable example is a heat engine using a single trapped ion in an electric field to convert temperature differences into controlled oscillations. Imagine running a tiny windmill powered by the chaotic breeze of molecular movements. This is the essence of energy conversion at the nanoscale. The basic structure of a nanoscale heat engine typically includes a working substance, such as a single trapped particle or molecule, thermal reservoirs at different temperatures to create a gradient, and an energy coupling mechanism like laser heating, magnetic fields, or electrostatic forces. These components operate under constraints where quantum tunneling, superposition, and non-equilibrium thermodynamics come into play. For example, in optically trapped nanoscale engines, laser light acts as both the energy source and the confinement mechanism. It's like a miniature steam engine where photons or electric fields replace steam to drive atomic-scale particles. Building functional nanoscale heat engines presents unique challenges. Thermal fluctuations dominate at small scales, making consistent energy flow difficult to maintain. Quantum coherence and tunneling can interfere with energy transfer processes, complicating predictability. Additionally, energy losses from friction and heat dissipation become significant due to the high surface area to volume ratio of nanoscale components. For instance, a nanoscale Stirling engine using a trapped bead in water faces substantial energy losses due to viscous drag, requiring precise feedback control to maintain efficiency. It's akin to trying to control a toy car in a hurricane, where every small gust of wind, thermal fluctuation has a massive impact on motion, making control extremely challenging. This highlights the difficulty in maintaining precise control over nanoscale heat engines. These engines operate far from thermodynamic equilibrium, where standard laws are modified by non-equilibrium thermodynamics. This field explains how systems exchange energy under fluctuating conditions, often using stochastic methods to model their behavior. A nanoscale Carnot engine, for example, operates under conditions dictated by fluctuations, deviating from classical Carnot efficiency limits. It's like running a race on a treadmill that randomly speeds up or slows down, requiring dynamic adaptation to unpredictable conditions. Quantum heat engines take this further by exploiting phenomena like coherence and entanglement to enhance performance. They utilize quantum states to achieve efficiencies beyond classical limits under certain conditions. Theoretical models predict quantum engines could surpass the Carnot limit by leveraging non-classical energy reservoirs. Quantum dots coupled to thermal gradients, for instance, act as quantum heat engines, converting energy fluctuations into controlled electron flow. This is like a quantum magician controlling energy flow, performing tricks that classical physics cannot replicate. Applications for nanoscale heat engines span energy harvesting, biomedical engineering, and sensing technologies. They could capture waste heat from microchips or biological systems to power nanodevices, drive molecular machines for drug delivery or cell repair, and enhance sensor sensitivity by converting small thermal fluctuations into measurable signals. A compelling example is their potential integration into implantable medical devices, converting body heat into mechanical energy to power sensors or drug delivery systems. This would be like fitting a power generator into a wristwatch, ensuring continuous operation without external batteries. Several experimental models have demonstrated the feasibility of these engines. Single-ion engines use trapped ions in electric fields heated by laser beams to perform cyclic motions akin to a piston. Colloidal systems utilize particles suspended in liquid, driven by temperature gradients to perform work. Quantum dots convert thermal gradients into electric currents, acting as nanoscale power sources. A recent experiment demonstrated a nanoscale Stirling engine where a silica bead trapped in an optical tweezer cyclically exchanges heat with two reservoirs, producing measurable work. It's like creating a microscopic version of a wind-up toy where precise movements generate useful energy. The efficiency of nanoscale heat engines is shaped by both classical and quantum thermodynamics. Stochastic effects at the nanoscale introduce deviations from classical predictions. Under specific conditions, nanoscale engines can achieve or even exceed classical efficiency limits by utilizing quantum correlations. For instance, quantum heat engines theoretically achieve efficiencies higher than Carnot efficiency by exploiting coherence in energy reservoirs. This is akin to turbocharging a car engine, not by burning more fuel, but by finding hidden ways to maximize existing energy output. The future of nanoscale heat engines promises revolutionary advances driven by nanotechnology and quantum mechanics. Potential developments include hybrid systems combining classical and quantum components, bio-inspired engines mimicking cellular processes, and engines synergizing with quantum computing to power or cool processors. For example, future nanoscale heat engines might harvest body heat to power wearable electronics, offering sustainable energy solutions. This would be like designing a car engine that runs on ambient air, creating energy without fuel dependence. Nanoscale heat engines represent a convergence of classical thermodynamics, quantum mechanics, and nanotechnology. These tiny machines challenge our understanding of energy conversion and promise revolutionary applications in energy harvesting, medicine, and computation.